In this video, we are going to talk about coordinate vectors, which is a fairly quick, easy topic to cover. And in fact, it's really just this one theorem/definition here that we are going to cover. And I will give you an example to illustrate this theorem. And then I will give you another example in a vector space other than Rn. And essentially, I will go through this overview slide and the examples, and then the rest of the video is essentially just providing a little more detail in the examples. Starting with our overview slide, this theorem, which gives us the definition of coordinates, let B be a vector space and let B be a set of vectors, which I denoted as vectors using the bold. So v1, v2, vn is a set of vectors that is a basis for V. So for each vector w in V, there exists a unique set of scalars, w1, w2, up to wn, the same number of bases, such that w is a linear combination of our basis vectors with w1, w2, up to wn as our scalars. And remember, we're saying this is a unique set of scalars. So given each vector w in V, there's a unique representation in terms of the basis vectors, and it follows these unique scalars then serve to characterize our vector w completely in terms of our basis B. In particular, we can identify our vector w unambiguously just by listing out our scalars. And then often we'll say then the coordinates of w with respect to basis B, and then we'll list the coordinates. And we call these unique scalars the coordinates of w with respect to B, and we call the vector w with the subscript b the coordinate vector of w. And for our first example, we chose R3, and the basis vector, the standard basis, that is 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. And this is chosen because the coordinates of any w with respect to this B1, the standard basis, is exactly what you think of as coordinates when you're plotting coordinates on a graph. But we will also take a different basis just for comparison, B2, where we have 1, 0, 0, 1, 1, 0, and 1, 1, 1. So what are the coordinates of the vector 2, 3, 1 in B1 and B2 using these two different bases? The first one in B1, as I said, you're used to this. The coordinates actually are 2, 3, 1 because it's 2 times the first standard vector, 1, 0, 0, plus 3 times 0, 1, 0, plus 1 times 0, 0, 1. So these are our coordinates, 2, 3, 1. In B2, and we'll work this out in detail later, but on this slide, 2, 3, 1 happens to be equal to negative 1 times 1, 0, 0, plus 2 times 1, 1, 0, plus 1 times 1, 1, 1, which means negative 1, 2, 1 are the coordinates in B2. Last, we can look at the vector space of polynomials of degree 2 or less, which we designate as P2. And we're going to use the basis 1x, x squared. We want to find the coordinates of the polynomial x squared minus 1 plus 1. And also this second polynomial, 2x plus 5. So the coordinates of our first polynomial, x squared minus 1 plus x, is 1, negative 1, 1, because this polynomial is equal to 1 times our first basis vector, which is 1, minus 1 times our second basis vector, which is x, plus 1 times our second basis vector. And you can see that this is exactly equal to our polynomial. For our second polynomial, 2x plus 5, well, that's equal to 5 times, where's our second? Yeah, 5 times our first basis vector, plus 2 times our second basis vector, plus 0, because there's no x squared terms, times our last basis vector. So the coordinates are 5, 2, 0. So this entire slide is the entirety of our video. What I will do next is just go through each step in a little more detail. First, just taking again that theorem and definition of coordinates. So let's let V be a vector space and B is a basis for V. So here's our vectors. We claim it's a basis, and if you recall, when I say the vectors of B spans a vector space V, the two things I'm saying about this set of vectors, B, is that B spans V. That is, any vector in the vector space V can be written as a linear combination of my bases, V1 up to Vn. So written out, any vector W is a linear combination of v1, v2, vn, where w1, w2, wn, those are just real numbers, they're scalars. The second thing that when I say that this set of vectors is a basis is that this set of vectors are linearly independent and they are the smallest spanning set. In other words, because they're linearly independent, you cannot make one from the others. So they are all necessary and to span the space V. And what this theorem tells us is that these scalars, W1 up to Wn, are unique. Because these scalars are unique, that means our vector W, we don't actually have to write out each vector. We can just list out the scalar multiples, and that will identify our vector W uniquely. In other words, it's understood that the first multiple, this first scalar here, goes with the first vector in our bases, and that the second scalar goes with the second vector in our bases. So we don't have to write this full linear combination out. We can just write our scalars. And these scalars are called the coordinates of W with respect to B. And sometimes it is understood what bases we're using, but if there's any doubt about what bases, we have to call out the bases because different bases will have different coordinates, or the same vector, W, will have different coordinates with different bases. And we call this vector here the coordinate vector of W. For our first example, we are going to consider two bases. Remember I said that coordinates are with respect to a basis. So here's our first example. We have two different bases. First is our standard bases. That is the basis of 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then we have the second basis, which starts out with 1, 0, 0, but then has 1, 1, 0, and 1, 1, 1. And the question is, what are the coordinates of the vector 2, 3, 1 in B1 and B2? And I will also mention that I chose B1 because this is the basis that you're used to. And when we talk about coordinates, it's totally consistent with what you are used to thinking of a coordinate when you're plotting points on the Cartesian coordinate plane, for example. So looking at B1, so we want to rewrite the vector 2, 3, 1 as a scalar times our first basis vector plus a scalar times our second basis vector plus a scalar times our third basis vector. So when we multiply and add these, what we get is W1, W2, W3. So W1 is going to equal to 2, W2 is going to equal to 3, and W3 is going to equal to 1. And so what we're saying is 2, 3, 1 is equal to 2 times 1, 0, 0 plus 3 times 0, 1, 0 plus 1 times 0, 0, 1, which means the coordinates in B1 are 2, 3, 1. So that was kind of like a lot more work. You could probably see it just by looking at 2, 3, 1. B2, our basis vector 1, 0, 0, 1, 1, 0, and 1, 1, 1 is a little bit harder, so we want to find a linear combination of our three basis vectors. x1, x2, x3 are our scalar multiples. That equals 2, 3, 1. So it's a little bit harder, but totally doable. And if you recall, to solve this system of linear equations, we use the coefficient matrix, so 1, 0, 0, the 1, 1, 0, and the 1, 1, 1. And then we have the augmented matrix by adding the solution 2, 3, 1 here. And we solve this system of equations by row reducing this augmented matrix. But fortunately, we're in the realm of textbook examples where this matrix is already row reduced. So remembering this first column represents x1, the second column represents x2, and the third column represents x3. So reading off, we get 0x1 plus 0x2 plus x3 is equal to 1. Our second equation tells us that x2 plus x3 equals 3, which means x2 is equal to 2. And then we have x1 plus x2 plus x3 equals 2, which tells us that x1 is equal to negative 1. I can plug that in. So 2, 3, 1 is equal to negative 1 times 1, 0, 0, 2 times our 1, 1, 0, and 1 times our 1, 1, 1. And you can see this calculation works out. which means 2, 3, 1. These are our coordinates in the standard bases. When we don't put a little bases index down here, it's understood we're using the standard bases. So 2, 3, 1 is equal to the vector -1, 2, 1 in using B2 here as a basis. And remember, we did say that our coordinates are with respect to a basis, and so we put the basis name here, B2. And this here is sort of an extra credit. It wasn't asked at all in this example, but I'm just going to do this as a quick review. So obviously 1, 0, 0, 0, 1, 0, and 0, 0, 1 span R3, since any vector A, B, C in R3 can be written as a linear combination of these three vectors, and also you can see that they are linearly independent. Well, actually, so we just showed that they span, and then second, they are also linearly independent. That's a different note, so therefore they do form a basis. The harder problem will be to show that 1, 0, 0, 1, 1, 0, and 1, 1, 1 span R3. But we can do this. To show that these three vectors span R3, we need to show that any vector, and we're just going to call it A, B, C in R3, can be written as a linear combination of 1, 0, 0, 1, 1, 0, and 1, 1, 1. So that's what I have here with x1, x2, and x3, my scalar multiples. And to solve this system of equations here, we're basically going to use the augmented matrix, that is my matrix of these coefficients, and then with my vector, my solution vector over here. I was getting ready to do the painful mathematics of row reducing, but then I realized this is already row reduced, which is good news. So again, this column represents x1, this column represents x2. I mean, you can see it right here in the equations, and this column here represents x3. So what we have as a set of linear equations, here we have 0 times x1, 0 times x2, x3 is equal to c. Here we have x2 plus x3 is equal to b, and then x1 plus x2 plus x3 is equal to a. So those are these three equations. Solving them with back substitution, we get that x3 is equal to c, x2 is equal to b minus c, and x1 is equal to a minus b. So these are our three coefficients that we would use if we needed to write a, b, c, some random vector in R3 as a linear combination of these basis vectors. And I did a little sanity check, and again, this is not any kind of proof, but just something to kind of make me feel like maybe my solution is correct. I used this vector 2, 3, 1, and then I said that's equal to, well, x1 is equal to a minus b. So this is a minus b. That would give me -1 in front of my 1, 0, 0 vector. My second coordinate, that's x2, and x2 is equal to b minus c. So this is b, this is c, so b minus c would give me 2 times my second basis vector. And then finally, my x3, my last scalar multiple, is equal to c. So I just put in 1 times my 1, 1, 1. And this checks out. So this gives me a good feeling for this solution here. And I just rewrote this out in this form just to be more explicit. So any vector a, b, c can be written as a linear combination of my basis vector 1, 0, 0, 1, 1, 0, and 1, 1, 1. And this is how I have shown that these vectors span R3. So far we've looked at our definition of the coordinates. We did this first example. So next we're going to look at this second example in more detail. And the example is for the vector space of polynomials of degree 2 or less, and that's denoted P2, use the basis 1x, x squared, find the coordinate of these two polynomials. Before we compute the answer to this problem, I want to back up a little bit and just look at this vector space of P2, which is polynomials of degree 2 or less. And first I want to remind you what it is to be a vector space, and that's a set of vectors, and vectors are a general idea. We're no longer restricted to Rn, and then they have an addition operation and a scalar multiplication operation. So certainly for polynomials, we know how to add two polynomials, and we know how to multiply a polynomial times a scalar. And to be a vector space, these 10 properties had to hold. And I am not going to go through the 10 properties because that would be exhausting. It would be exhaustive, but it would also be exhausting. So I will just look at closure property, and I will prove the commutative property of addition. I'll tell you about the additive identity, and the rest I'll leave for you as an exercise if you'd like, or you can go back and review the other video where we covered this topic for vector spaces. But I just want to remind you what it is to be a vector space and kind of assure you that P2 is a vector space. And actually, in general, Pn, that is the space of polynomials of degree n or less, those are all vector spaces, and the proof is sort of similar. And I said I would start by proving the closure property. So if we have two vectors and we add them together, they are still going to be in V. So two vectors, so two polynomials in our space of polynomials look like this. Maybe P1 is equal to A1 plus A2x plus A3x squared, where A1, A2, A3, they're scalars. Then another polynomial that's degree 2 or less would be P2, which is B1 plus B2x plus B3x squared, where B1, B2, and B3 are scalars. If we add them together, we are going to get P1 plus P2, which is A1 plus A2x plus A3x squared plus B1 plus B2x plus B3x squared, which is equal to grouping our like terms together, A1 plus B1, A2 plus B2 times x, A3 plus B3 times x cubed squared, which is still a polynomial of degree 2 or less, and therefore our addition is closed. Looking at our scalar multiplication here, so alpha, we're going to say alpha is a scalar, times P1, our first polynomial, is alpha times A1 plus A2x plus A3x squared. And remember, A1, A2, A3 are also scalars. So by our multiplication, our normal multiplication of polynomials by a scalar, it's A1 times alpha, or alpha times A2 times x plus alpha times A3 times x squared, which is still a polynomial of degree 2 or less. So the scalar multiplication is also closed. To prove that this addition between vectors is commutative, I took my P1 and P2, my two polynomials of degree 2 less, and I add them together, which is equal to A1 plus A2x plus A3x squared, plus B1 plus B2x plus B3x squared, and I combine my like terms as we do when we do polynomials. I can, because addition of, here at this point, B1 and A1, they're real numbers, so they commute. This also commutes, and these are real numbers, so they commute. And so now, by the way we add polynomials, grouping our terms together, ungrouping like terms, I can have B1 plus B2x plus B3x squared plus A1 plus A2x plus A3x squared, which is P2 plus P1. So I have shown the addition of the two vectors are commutative. The last property I was going to go through was just to identify the additive identity, which is equal to the 0 polynomial, which is 0 plus 0x plus 0x squared. And I can show if I add it to a polynomial P1, I have my P1 polynomial times my 0 polynomial. I group like terms and I get back P1. So that was another little extra credit exercise. Since this was a short video, I thought this was a good opportunity to explore P2 a little bit more. There is one more thing I want to say about 2, which is a natural basis for the polynomials. Just like there's a natural basis for our vectors in Rn, which is the standard basis, there's a natural basis for polynomials of degree n or less. So for n equals 2, the basis is 1x x squared. So 1x x squared is a basis for P2. If you like, you can think of 1 as 1 plus 0x plus 0x squared, and x as 0 plus x squared, and then x squared is equal to 0 plus 0x plus 1 times x. And then any polynomial of degree 2 or less can be written as a linear combination of 1x x squared. In particular, let's just take our example polynomial. P1 is equal to A1 plus A2x plus A3x squared, whereas A1, A2, A3 are all scalars. Then what we can see is that this polynomial obviously is written, in fact, that's how we write it, as a linear combination of 1, that's A1 times 1, A2 times x, and A3 times x squared. So in other words, our 1x x squared spans the space P2. And this last statement I'm going to hand wave a little bit, but 1x and x squared are linearly independent, and you kind of know that because you can't write any in terms of the others. In other words, 1 cannot be written as a linear combination of x and x squared. X cannot be written as a linear combination of 1 and x squared cannot be written as a linear combination of 1 and x. So they are linearly independent. And hence, our 1x, x squared is a basis for P2, and again, this is the natural basis. Similarly, 1x, x squared, x cubed is a basis for P3, polynomials of degree 3 or less. And just as in Rn there are other bases than the standard bases, in P2 there are other bases than the standard bases here that we looked at. And now our two problems of writing the coordinates of P of x and P2 of x is fairly straightforward. Writing our first polynomial x squared minus x plus 1 as a linear combination of our basis vectors 1x and x squared, I have 1 times our first basis vector 1, I have negative 1 times our second basis vector x, plus 1 times our last basis vector x squared. So this will equal to P of x. That means our coordinates for this vector here, this polynomial x squared minus x plus 1, is equal to 1, minus 1, and 1. Similarly, writing P2, which is equal to 2x plus 5 as a linear combination of 1x and x squared, we get 5 times our first basis vector 1 plus 2 times our second basis vector x plus 0 times our last basis vector x squared, which means our coordinate is going to be 5, 2, and 0. Summarizing what we did in this video, we defined what a coordinate was, a coordinate of a vector w with respect to a basis b. So if we had a vector space v and we had a basis for that vector space, which was b, a set of vectors v1, v2 up to vn, for each vector w in v, there would be a unique set of scalars w1, w2 up to wn such that w was a linear combination of the basis vectors times these unique scalars. And because these scalars are unique, they can uniquely represent any vector w. So instead of having to write out the entire linear combination, if we understand what bases we are using, we can just write the scalar multiples, and that would be a vector of scalars, which we call our coordinate of w with respect to b. And this often we put the little b here to indicate what bases these coordinates are with respect to. We took two examples. The first one was about R3, where first we compared the standard bases vectors, and then we did a second basis for R3, which was 1, 0, 0, 1, 1, 0, 1, 1, 1, and we wrote the coordinate 2, 3, 1 in bases b1 and b2. So in b1, well, because this is the standard basis, it very naturally turns into coordinates 2 times our first basis vector, 3 times our second basis vector, and 1 times our last basis vector. So basically 2, 3, 1, those are the same coordinates in the standard basis. Again, this is natural. In b2, we can see, and I worked this out so you could, using this matrix, but what we ended up with is that the coordinates would be negative 1, 2, 1, because 2, 3, 1 is equal to negative 1 times our first basis vector plus 2 times our second basis vector plus 3 times our last basis vector. And in this case, our coordinate is negative 1, 2, 1, and we either need to put that little subscript b2 down here or just say the coordinates in b2 are. We need to, again, explicitly say, if we're not using a standard basis, we need to say what bases these coordinates are with respect to. Last, we looked at the space of polynomials of degree 2 or less, and we did go into a little more detail about P2, and we looked at the vector space itself, and we used the bases 1x and x squared to find the coordinates of these two polynomials. The first one, x squared minus 1 plus x, the coordinate was 1, 1, negative 1, 1, because this polynomial is equal to 1, this is our first coordinate, times our first basis vector, plus negative 1, that's our second coordinate, times our second basis vector x, plus 1, our last coordinate, times our last basis vector x squared. Similarly, P2, we found the coordinate was 5, 2, 0, and we did do the calculation for that, or kind of showed it more explicitly. And the coordinate's 5, 2, 0 because this is 5 times our first basis vector 1, plus 2 times our second basis vector x, plus 0 times our last basis vector. And that was it for this video. Thank you for watching.